Hello and welcome. This is Answer Everywhere. We do sight readings of source code, like you would sight read music, source code we've never seen before, and we try to understand what makes it tick. And today, I thought we would look at the Vulkan API layer. This is a part of the graphics layer. We've looked at a lot of graphics-related stuff, GPU-related stuff, I would say, including video games that use the GPU as God intended to render graphics onto the screen. We've also looked at the GPU from a computational perspective. We have a video about the XLA compiler that compiles like machine learning code into kernels that run on the GPU and so forth. We've looked at many machine learning libraries as well. We have also looked at some Verilog for like toy GPU hardware. But I think personally, I feel like there's a gap in my understanding. I don't, maybe not a gap, maybe just a lack of integration of all of the individual pieces. But I thought that one thing that I especially feel like is a blank hole in my understanding is the kind of API layer. If you were to write a modern app and send off API calls, what is actually happening? What's the difference? For example, if I have an image of myself on the screen, it has a bunch of pixels. It looks a little bit like a painting, versus some apps like draw circles and spheres and like geometric objects. Is that all the same? Is that all going along the same path? Are those going along different paths? Are those done by the same chips? So those sorts of questions. I figured that it would be good to look at the API level. Now, ordinarily, we look at code. I'm not entirely certain how Vulkan is broken down. I know that it's primarily an API. I know that they have an SDK. I believe the SDK is open source. But even if we look at the SDK, I'm not sure how much of the meat is happening in the SDK versus like, is the SDK like a thin proxy wrapper for a bunch of drivers and the work is all done in the drivers? I don't know. So I thought we would poke around Vulkan and see what we can see. And that's it. That's all I'm going to tell you, because that's all I know. I will pop out this chat, which I've popped out twice now. I don't know why it keeps popping in. I don't know if this is a YouTube bug. It's probably a me bug. All right, so here's the Vulkan docs in the sense of documentation. We've got XML, an XML API registry. I'd like to see that. How old is Vulkan? I feel like Vulkan is newer than the retreat away from XML. Oh, I wikied XML. How about Vulkan? Vulkan. The stable release. Okay, so the initial release is 2016. I feel like XML was out of favor by then, but I'm not, it's still used in graphics and stuff sometimes. Okay, so let's take a peek at the at like what they think of as the documentation. We have build tests and chapters. So this is some sort of book, I guess, of documentation. We have images. We have includes. I have no idea what Antora is, but it has ant in the title, so I'm going to look at it. KTech, I think is related to LaTeX. No, it's a village. Is cross-browser JavaScript library that displays mathematical notation in web browsers. Okay. And we have proposals, which will be probably like proposals for extensions of the API and that sort of thing. We have scripts. I'm going to guess. Hello, Bot Eater. Welcome. Bot Eater, do you know anything about graphics? I feel like you probably do from our previous conversations. And then we have tests. I'm guessing these are like all tests and stuff in the sense of rendering the documentation, as opposed to anything code related. Here are chapters. I mean, this is looking good. We've got tensors. We've got dense geometry format. We've got acquire DRM display, acquire xlib display. Metal objects. I think metal is probably the Mac OS one. Google Display Timing, GGP, Stream Descriptor Surface. Fuchsia is the Google OS. I don't know if it's still in progress. I don't know what GGP is. Maybe an operating system, maybe a graphics. It's the gateway to gateway protocol for routing datagrams. I doubt that's it. GGP Stream Descriptor Surface. How about graphics? A bit from my childhood in times of... Okay. That's probably helpful. Sometimes having the... I don't know when your childhood was, but sometimes having the older information is useful for understanding the new information because stuff evolves. So let's see if we can figure out... Okay, Google Games Platform. That's fine. That's not what I need. Okay. And I'm not sure, really... I mean, we don't normally read documentation on this channel. I read documentation, but that's not what we do here. And then here's the include Vulkan. And we have like Vulkan.h. Is this an actual honest to goodness header? Or is this... it seems to be including other headers. I don't know if this is for compiling like LaTeX documentation. It's Apache 2.0, Vulkan core. Let's see if we can find Vulkan core. Is it like that? Here's the XML README that mentions Vulkan core. Registry, build instructions in node, build environment, blah, blah, blah. Okay. Video headers. In addition to vk.xml, this directory also includes video.xml. This is a similarly structured XML file used to produce headers for structures and other types. Standard video star associated with externally defined video standards. So is this producing the actual headers you depend on? One moment. Okay. So we've got XML files. We're building something. But what are we building? Are we building the universe we want to live in? vtest. Yeah, I think this is actually compiling stuff. It is used to generate the canonical Vulkan header files. The API ASCII doc include files used by the Vulkan specification and reference pages, and many others. So the API ASCII include files is the next separate thing in a list. It's not modifying or describing what the canonical Vulkan header files are, I believe. So I think that the canonical Vulkan header files are C code, or at least a bunch of headers. Antora. Let's see if we can find out what Antora is. Antora builds and deploys thermal energy storage. Wow. To deploy always-on industrial operations with low-cost energy. Very cool. But that's not what this is. Antora is a tool that lets you create, manage, and publish documentation sites composed of ASCII doc files from one or more repositories. Okay, so this is some thing that I don't think this is the implementation. I think this is probably the configuration for some tool that weaves together ASCII doc files and what's the word? Publishes them as a site. Here are proposals. These are different things that you could conceivably be made into the spec. There's some stuff for ARM, lots of stuff for Android, anti-lag in AMD, a shader in NQ for AMDX. Okay, mesh shader. I don't know what XT is. I don't think it's the file system. The rasterization pipeline for Vulkan is fairly fixed. A fixed input stage assembles vertex data for the vertex shader. Data optionally passes through tessellation and geometry stages. Cool. In fact, what we're going to do is I purposely didn't clone this repo because I thought we would not actually be needing it, but let's clone it so that we can inquire about it on the command line and stuff. You know, all that stuff. Okay. So this is actually somewhat interesting. I think maybe unintentionally, this is just background for this particular doc. This is not what the doc is about. but this is telling us about the rasterization pipeline. Then fixed vertex processing passes the resulting primitives to the rasterizer. Okay, so we start with vertex data for the vertex shader. So these should be basically triangle vertices. Data optionally passes through tessellation. So a tessellation, at least in math, is like a tiling in polygons. Is it necessarily triangles? Is it necessarily unbounded? A tessellation or tiling is the covering of a surface, often a plane, using one or more geometric shapes, called tiles, with no overlaps and no gaps. Tessellation can be generalized to higher dimensions and a variety of geometries. Here's a tessellation. It's cool. Okay. So there's no requirement that they even be polygons. That's fine. They probably are in the GPU world. All right, then fixed vertex processing passes the resulting primitives to the rasterizer. Okay, I don't know what the tessellation stage is doing. I guess some sort of tiling. Maybe, I guess the idea is maybe that you give it some vertex data for some, like if you want to tile the whole screen and and you just have like 4 tiles, you just maybe give it the information for those 4 tiles, and then there's a tessellation process on the GPU or in the API somewhere that does the tessellation for you rather than you copying everything everywhere. I'm guessing is possibly what it does. And then whatever a geometry stage is, that might include things like surface normals, smoothing. I don't know. Bob Eater is saying, I wonder if the tessellation stage is how it deals with said vertex data. Yeah, I think in a sense, but we'll find out more about it. Then fixed vertex processing passes the resulting primitives to the rasterizer. Okay. As the rendering engines get increasingly complex, this fixed nature has become a bottleneck. Okay. So, and I'm not even really sure what rasterization is. I think it's like, first of all, let's get rid of these. I don't think we need to generate tags, do we? Let's just start Gemini. Okay. We'll get to that later, that part of the code. I feel like rasterization is drawing things with dots. Is that basically it? Rasterization is the task of taking an image described in a vector graphics format. Okay, so it's necessarily like a map from vector graphics to like a raster image. Is that the idea? And maybe in this context, what it means is that the vertex data is in a sense like a vector description. It's turning stuff into pixels, surely. Okay. So I guess this must always be done. Is this always done for, it must always be done because the screen is always pixels. So I don't know what it means for, whoa. Stop that. For something like SVG, where you have this rescaling property, I guess the idea there is that maybe just rasterization happens later, and you can like zoom in and get infinite detail because it's always going to raster. It's always going to somehow figure out what portion of the graphic is inside of your view screen and rasterize that, as opposed to rasterizing the image ahead of time, where when you zoom in, you're like zooming in on individual pixels or whatever. Every frame, so Bot Uter says every frame, I'm pretty sure it's the phase before the fragment shader. Rasterization is? Okay, so this is rasterizing some triangles. So triangle rasterization, polygons are a common representation of digital 3D models. Before rasterization, individual polygons are typically broken down into triangles. Therefore, a typical problem to solve in 3D rasterization is rasterization of the triangle. Okay. I mean, it's pretty ugly. because it's this is, you can actually see the grid that they're using. And so this is what, like maybe the 50 more than 50%, you go to the color. So if you have two colors, you go to the one with the highest percentage maybe of color. Although no, because here, like, I don't think I can stop this, but yeah, I can. No, I can't. Here, it looks like the highest percentage is red, but it gets turned into yellow. So the algorithm is more complicated than just taking majority rule. You want to leave no holes between the triangles so that the rasterized area is completely filled. No pixel is rasterized more than once. So they don't overlap. This is to guarantee blah, blah, blah. And then this leads to established rasterization rules. To guarantee the above conditions, one set of rules is called a top left rule, which states that a pixel is rasterized if and only if its center lies completely inside the triangle, or its center lies completely inside the triangle. As opposed to what? Being on an edge? A center is a point. So it's either in a triangle or it's on an edge. I guess, or it's a vertex. Its center lies exactly on the triangle edge. That is, or in case of corners, all are either the top or left edge. So is the reason that here, I guess, okay, so here this pixel becomes yellow because I think the center is inside the yellow triangle, is my guess. Okay, so that's rasterization. You guys all knew that. I didn't know it. It may, yeah, that's right. It may choose the color that's closest to the center. Okay, so I did know that before. I'm just kind of refreshing my memory about what all these different things mean. Okay, so now we have this rasterization pipeline. I don't know what the tessellation part of the GPU is actually doing, but let's figure that out. Is the dividing of data sets of polygons, is it just triangulating the polygons? Okay. What? I don't think. Yeah. So I'm guessing what it says is, what it's saying is that we can give it the vertices for any kind of polygon. I was thinking we give it triangular vertices of triangles, but it sounds like you just give it any of the polygonal vertices, and then the GPU is responsible for triangulation. Is tessellation just the same as triangulation? Is the dividing of data sets of polygons, sometimes called vertex sets. The dividing of data sets of polygons, sometimes called vertex sets, representing objects in a scene into suitable structures for rendering. Okay, data is tessellated into triangles. The key advantage of tessellation for real-time graphics is that it allows details to be dynamically added and subtracted from a 3D polygon mesh. Okay, we have seen this in Blender, although it wasn't clear to me in Blender like where all of this stuff was taking place. But in something like Blender, if you want to smooth a surface, you can model it in lower polygon stuff, and then there's like triangulation that happens under the hood for smoothing and whatnot. I forget what that's called. I don't know the right keyword for that. A triangle is made of 3 vertices, says Spot Eater. You can choose how those vertices are interpreted. Can you? I don't know if that's true. So 3 vertices will necessarily define a plane if they're not coplanar. I guess you can, maybe you're saying that like, you could think of them as being vertices, or you can think of them as like another 3-point parameterization of a triangle. I would believe that. Okay. All right. So what have we learned? So that's about the rasterization pipeline. Let's see if we can find more about pipelines. That seems like the place to be. In fact, I should not have searched with an S on pipeline. How about just pipeline? Here's config chunkindex lunar.js, pipeline binary, pipeline properties for VK KHR. I'm guessing KHR is another system because these 3-letter codes have been so far like operating systems or probably really hardware, split up by hardware. Here's a Vulkan object.py script. I don't know if this pipeline is for documentation processing. So why don't we, instead of just searching for pipeline, let's search for rasterization and see if that can like point us to a directory. KHR line rasterization. How about AMD? I think I have AMD stuff. But the way they link. Okay. I see. So there's some options in the draw call that that specifies how they link up. Okay. I'll see if I can find some of the draw calls. That's kind of where we're going, is looking for the actual API calls eventually. This extension, so this is an appendix. This is rasterization order. Let's get out of this. Let's go back to chapters. And here we see what we want. So let's go to this lunar.js, whatever that is. I don't even think it's real. Here's tessellization, textures. Textures make sense to me. I'm guessing I think a texture necessarily is not triangles. It's maybe like pixel by pixel. And then you have just some map of the different, you just have some indication of the different pixels and you have information that applies pixel-wise, is I think basically the idea of a texture. Video coding. This might be turning the, I don't know, maybe producing videos from individual frames. I do want that, but I don't want it yet. We'll look at vertex post proc. I think we opened up textures, sparse mem. I'm guessing maybe sparse memory. Shaders. I don't know, for example, off the top of my head, where do shaders happen after rasterization? Ray tracing. I also don't know when that happens. Ray traversal. I'm not sure what that is. Render path might be render might be like the whole pipeline, and a pass might be like an individual pass, of which like rasterization is one, or it might be something different. I don't know what its resources are. Samplers, I'm going to guess, is for sampling things, like in the sense of statistics, like taking a smaller number to determine something. Pipelines has its own doc, memory, limits, images, initialization, interfaces. Introduction might be good. Look at geometry though. Frame buffers, all of this stuff. We'll look at it all. Dispatch, drawing, extensions, Excel structures. Excel as in accelerate, not in the sense of like Microsoft Excel. Not in the sense of excelling at anything. Capabilities. I don't know what this capabilities is. It might be like platform specific stuff. I doubt it's like a capability based authorization system. Excel structures. I'm guessing acceleration in the sense of physics. All right, let's see what we got. Tessellation. Tessellation involves 3 pipeline stages. First, a tessellation control shader. Let's pop these out one at a time just in case we get like super deep in the stack here on any one of these. I'm going to try to do them quickly, but you never know. So tessellation control shader transforms control points of a patch. I don't know what a patch is. I'm guessing a patch is maybe like a patch in the sense of manifold theory. It's like a map of a possibly 3-dimensional structure that's kind of splayed out in 2D space and can produce per patch data. Second, a fixed function tessellator generates multiple primitives corresponding to a tessellation of the patch in UV or UVW parameter space. So UV are the common names of coordinates given in for parameterized surfaces. UVW now has 3 dimensions. So this is no longer a surface. It's some 3-dimensional object, but I think that this suggests that my understanding of patch is correct. Third, a tessellation evaluation shader transforms the vertices of the tessellated patch, for example, to compute their positions and attributes as part of the tessellated surface. To compute their positions and attributes as part of the tessellation. Okay, so the tessellator is enabled when the pipeline contains both a tessellation control shader and a tessellation evaluation shader. Okay, so the tessellation control shader transforms control points of a patch. We don't know what a control point is yet, or I don't. So if I click on tessellation control, so let's see if we can find Vulkan control point outside of the repo here. This sample demonstrates how to use VK extended dynamic state. Changes how patch control points are managed. Instead of static description during pipeline creation, this extension allows developers to change the parameter by something. But what is a control point? Can you tell me? No results? What if we look here? All right, I have only one thing left to try, and that's ask the AI. I forgot to ask Vulkan. And Bot Eater is saying, so the tessellation part produces the triangles? Yeah, I think that's what we saw in the Wikipedia article, that it's tessellation is the same as triangulation. So you're giving it, in the Wikipedia image example, it was like a box. What is a box called? A cube. Cube. And it's going to do things like, obviously you can take each face of the cube and draw a diagonal, and then each face becomes a 2-dimensional triangle. You need 3-dimensional triangles, and I'm not sure what the minimum number of like additional edges you need to do that is, but it's some number. In the Vulkan graphics API, control points are a key component of the tessellation state. That doesn't tell me anything. Why are you highlighting this? They define the input vertices of a geometric patch, which are then used by the tessellation shaders to generate more detailed geometry on the GPU. The input vertices. Okay, what does that even mean? So a geometric patch, is a like a chart in manifolds? And if so, are you saying that a control point is literally just a vertex that you input? They are not singled out as special vertices in the input. This may be too complex for the Google AI search. Is related to, but not the same as a chart in manifolds. The difference is the approximations versus exact representation, blah, blah. Okay. Well, yes, it's a computer. It doesn't have the real number system built into it. Okay. So are control points just normal vertices? Yes. In the Vulkan pipeline, control points are the input vertices that are passed from the vertex buffer to the tessellation control shader. They are not inherently special in the initial input data itself. Okay. You define the control points using the same vertex buffer mechanisms you use for normal vertices, positions, normals, UV coordinates, etc. The graphics pipeline is configured to treat the incoming data not as a series of triangles or lines, but as patches of a specific number of control points. For example, 3 for a Bezier triangle patch, 4 for a Bezier quad patch. The specialness comes from their role in the tessellation shaders. Okay. So I don't know what a Bezier triangle patch is, but it must be some use of Bezier curves to create a triangle. Like this. So is it like a bulky triangle? It needs 3 vertices. So this has P1, P1's here, P0 and P2, each with different normals. And these normals all look the same length to me. But after some process, we get this. We have like a new center. We've triangulated, and there's an arch. What's the word for the computation architecture? Or like generative or geometric? Yeah, this stuff. Bus stop. I could have sworn, but how about the Sydney Opera House? Can you ask if it's before or after the vertex shader? I will ask that. So these little things on the Sydney Opera House seem like they may have been created with Bezier triangles. Yes, procedure. Is that what it's called? Procedural. Okay. And you wanted, you wanted me to ask, is this before or after the vertex shader? I assume you mean, is tessellation before or after vertex shader? I'm pretty sure we maybe saw that it was before. Oh, tessellation comes after the vertex shader stage. So the vertex shader is the mandatory stage, processes the raw input vertices, transforms them and outputs them to the next stage. Okay. When tessellation is active, it outputs control points in a buffer-like structure. Okay, so so shaders don't necessarily have to do any sort of shading, right? It's just anything that's operating on the GPU. What is a Bezier triangle? Okay. Shading language. So a shader is a programmable operation which is applied to data as it moves through the rendering pipeline. And they can act on vertices. Yeah, so there's nothing in particular about shaders. Here's an example of I think what Bot Eater was asking. We have some input assembly. In this case, it's a triangle. I'm guessing it doesn't actually have to be. The vertex shader does something. I don't know now the triangle's rotated. Tessellation is going to divide, even though it was a triangle, it's going to divide it into even more triangles. The geometry shader is doing what? It's maybe attaching another vertex. Although why isn't this as triangulated as the rest of the triangle? I don't know. Rasterization is going to take this triangular thing and turn it into a blob. Fragment shader seems to be coloring it, although I don't know if that's supposed to be what it's doing. And then it's going to do color blending, which seems to just have colored the rest of the background. Here's the Stanford Dragon model, which I'm actually not familiar with. I'm familiar with the bunny model, but this is what? Rendered using fragment shaders with different outputs, solid white, applied texture, and physically based shading. Okay, so maybe the fragment shader is so called because it operates on fragments. So for example, here with a test texture. So here we seem to be able to see the individual patches is maybe what's going on. And maybe this is the sense in which it's fragmentary. Fragment shader runs per pixel. Okay, well maybe I'm wrong. I don't know. Fragment shaders, also known as pixel shaders, compute color and other attributes of each fragment, a unit of rendering work affecting at most a single output pixel. Yeah, you're right. A fragment of what? I guess it's maybe a I'm just trying to think about the name. Is it just like is the idea that it's like a fragment of the higher dimensional space that, in a sense, is upstream of the pixel? Simplest kinds of pixel shaders output one screen pixel as a color value. More complex shaders with multiple outputs are also possible. Okay. I'm going to need a better AI. So a Bezier triangle is a typical type of Bezier surface that uses a set of control points arranged in a triangular mesh to define a smooth, curved surface. Okay, so Bezier surface. I feel like I have heard of Bezier surface. I don't know if I ever remembered what it was or looked into it. Okay, so it's a generalization of Bezier curves, which was obvious. I just didn't know what a Bezier triangle was supposed to be. And so we've got control points, and we have some way of, I assume doing like interpolation. It's given by, so you have some parametric surface, and you, where the position of a point P as a function of the parametric coordinates UV is given by, we've got these BNI and BMJ and Kij. Kij looks like a vector. No, those are the points. Okay. And then U and V are just general coordinates. And these are like weighted sums, weighted double sums of the Kij points. And then what are the B functions? This must be B for Bezier. Bezier? Okay, so evaluate over the unit square where B upper n sub I of U, it's a function of a single variable, and we're getting two variables by summing over the two invocations of different ones, is we're going to do n choose I, take the single argument u to the I, and then 1 minus u to the I, n minus I. So this looks like a binomial coefficient. Is a basis of the Bernstein polynomial, and it is a binomial coefficient. No, this is the binomial. This looks like what's it called? The is it the binomial probability distribution? This, yeah. Okay. And then whoever Bernstein is a polynomial expressed as a linear combination of Bernstein basis polynomials. After Sergei Datanovich Bernstein. Sounds Russian. Soviet. Ukrainian? Oh, sorry, Ukrainian. Okay, great. These look like binomial. And then to evaluate any f of x, we evaluate f at one of the n lattice points close to x randomly chosen by the binomial distribution. Okay. The thing, yeah, something about statistic in the polynomial distribution. Yes. So why are the curvy stuff Bezier triangle near fixed edges of the triangles? That's weird. So why are the curvy stuff near the fixed edges of the triangles? I'm not sure I understand. Oh, you're asking like from the statistical perspective, are you asking why is the curvature highest? Like why is it steepest by the fixed edges? I assume that's because as you're getting close to the edge, somehow you are summing over you have less input from the other vertices. So the middle is kind of the highest because that's where you are getting the most input from all of these vertices. And if we look at the binomial distribution, It's like discrete normal. And I assume those two facts you should be able to develop an intuition for why it's tallest here. And so I think that maybe what your question was is the it's most curvy, it's least flat along the edges. Yeah, God, I love math. Yeah, math is cool. Math is life. So I do have some other AIs open. I don't know if we need them at this point. I'm learning. I'm not really looking at code, but I am learning. Oh, but I wanted to know about procedural architecture. I'm not positive that's what it's called. Yeah, maybe it is. But if it was, there would be a Wikipedia article. Procedural generation. Computation architecture. Computer architecture, no. How about computer-aided geometric architecture? How about we just ask AI? What is the name of computer-generated geometric architecture that uses constraint solvers to design organic or unusual structures? We'll ask the Google. Computational design or parametric design? There's some other name for it. Maybe computer-aided architectural design? I'm not finding it. I don't want to. Let's ask ChatGPT. But I wonder why even bother with it? Can't the device just draw the triangle? The device can draw the triangle, but I think the idea is that you want to say that you have a curve by like in the case of the Bezier triangle, you want to say you have a curve, but you want to really just give it shadow and say like make this like a 3D-ish looking thing based on like its what the thing it would project onto the floor. It basically looks like a tent. I guess I guess this is a quadrilateral, but you don't even have to have the edges don't have to touch the floor, but it looks like a tent, right? I don't know why. I'm sure it's useful, but like maybe if you have lots of them for modeling, it's especially useful. But it's a way of giving the GPU, I think, less data and having it produce a visually pleasing 3D data. Computational architecture, constraint solvers, geometric constraint solving, blah, blah, blah. Parametric modeling systems. Algorithmic architecture. Let's try, I think I tried generative. And let's try algorithmic. I swear this is a field. Maybe it's not a field anymore. Yeah, this looks good. Generative design? Is that my problem? Let's try generative design. This looks promising. No. All right, I give up. It's called something. If you know what it's called, let me know. Let's see if there's a Wikipedia entry on generative architecture. No. Fine. I give up. There's algorithmic architecture. This looks cool. I don't know if you want to live in any of these spaces. I bet there's not also a Wikipedia article for this. No. I think we all know that everyone secretly wants to live in a geodesic dome house. Why would you not want to? It's basically optimal. Look, it looks like a helmet. All right, that was a detour. That was a detour, but back to work, back to play, I guess. Okay, so the tessellation, we've got this control shader thing that does seems to be doing Bezier surfaces and stuff. I don't really know how to pronounce Bezier or Bezier properly, but and then we have a fixed function tessellator generates multiple primitives corresponding to a tessellation of the patch. I don't know what a primitive is. I'm guessing that this is maybe just a way of saying that we've got a tessellation and now we have like the objects that the GPU wants to see that corresponds to them. So like once we've triangulated, maybe these are triangles or lists of vertices or whatever. And then a tessellation evaluation shader transforms the vertices of the tessellated patch. So we've tessellated the patch. We've got some vertices from the second thing, I think. For example, to compute their positions and attributes as part of the tessellated surface. So I'm guessing what this is saying is that we have, after tessellating, we've chosen essentially a coordinate system where we're dealing with the plane and the origin's probably somewhere close to the middle. And then here it's saying that these are really parts of a patch of like, who's the guy from Toy Story? Let's say Woody. This is really the patch of Woody's hat. And so it can't be in the origin in the middle of the screen. It's got to go to wherever Woody goes or something like that. The tessellator is enabled when the pipeline contains both a tessellation control shader, which is, I thought, just for Bezier curves, and a tessellation evaluation shader. Okay. If a pipeline includes both a shader and blah, 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 blah. Tessellation execution modes include code triangles. I don't know what code means, but this is some sort of choice you have between triangles, quads, and ISO lines. And this might be what similar to what BotUter was saying. Oh, I missed this question. An orientation in space, like if you had a triangle a bit rotated on the y-axis, it would need to look like it's smaller in a way. Rotated in the y-axis. Oh, I see what you're saying. Like if you tilt it backwards? Yes. That I think that would be part of the third thing, because I mean, normally when you give something UV coordinates, you're like position in a sense positioning the camera right over it, and I think that's like projectivization, I guess. I don't know if that's part of the if it's done anywhere in this pipeline. My guess is it would be here, but I really have no idea. But yes, you're right. So ISO lines. So ISO means same, right? These should be lines of same something or other. Okay, sure. These are like an they're not really lines. Is that what? I don't feel like we call these ISO lines, do we? A contour line. Yeah, I guess we do use line for curve. So it may be something like this where you're defining. I don't know when you would use this. Vulkan. I'm not sure. I'm not going to go into ISO lines, but for some reason, that's one of the things you can put in. I guess you can, if you have a thing built up of ISO lines, you can tessellate it. Why not? These control the type of subdivision and topology of the output primitive. One mode must be set. Okay. And then we have, I don't know, we are on a second bullet point. I don't know what the second bullet point means. But we have something about vertex order, clockwise versus counterclockwise, it looks like. We have a point mode that controls generation of points rather than triangles or lines. Okay. I don't know why you would generate points, but you can do that. And then we have spacing equal versus spacing fractional even, spacing fractional odd. Controls the spacing of segments on the edges of tessellated primitives. The spacing of segments. I'm not sure. It's like, I feel like we've triangulated, so now we have edges of triangles. I don't know how they can be spaced. But I don't know what that means. I don't know if I don't think it's saying that there can be gaps between them, but who knows? And then we have output vertices. Controls the size of the output patch. For triangles, the tessellator subdivides the triangle primitive into smaller triangles. For quads, the tessellator subdivides the rectangle primitive into smaller triangles. For isolines, the tessellator subdivides a rectangle primitive into a collection of line segments arranged in strips stretching across the rectangle in the U dimension. Okay, so you give it a rectangle primitive when you're in isoline mode. And what you get are line segments arranged in strips. So like teeth. So some subdivided rectangle. I'm guessing U is X. So in the X direction. I.e. the coordinates encode test coord of the form 0x through 1x. Okay, for all tessellation evaluation shaders. Okay, so that's what isoline mode does. It's kind of like not a grid, but a half grid or something, it sounds like. Each vertex produced by the tessellator has an associated UVW and UV position in a normalized parameter space. Okay, great. So that's tessellation. Here's spacing. Each of the tessellation levels is used to determine the number and spacing of segments used to subdivide a corresponding edge. Okay, so these are spaces in the sense that you're going to subdivide. So it's like maybe the fineness of a mesh. Okay, cool. That's tessellation. Let's see what else we see. Isoline sounds like a Disney supervillain. I don't know. Does it? Isolines. I don't know if I believe that. Who are the Disney supervillains? Cruella de Vil is like literally named Cruel Devil. And I'm blanking on all the villains. There's like one per movie, right? Okay. Here's textures. Where does texturing happen? So Vulkan image operations are operations performed on images by spur v image instructions. Spur v. I've seen this a bunch of times in this repo. I don't know what it means. Standard portable intermediate representation. So it's some intermediate language for parallel computing in graphics by the Koorosh group. Okay. It's to natively represent the primitives needed by compute in graphics to separate high-level language from the interface to compute in graphics drivers. So what are some examples? I don't know. It's some sort of intermediate representation. I'm not sure what it's going to look like, but we do have shaders maybe. Graphical shaders are structured control flow in spur v to state how control flow nests. This helps in defining divergence and reconvergence of control flow on parallel execution environments. Okay, and there's stuff about linking capabilities. Great. So the image operations generate some or operations performed on images by the spur v image instructions, which take the code type image representing an S name image VK image view or op type sampled image. I don't know what that means. It's just telling us what the things are called. But we have some stuff about coordinate systems. Unnormalized sampling coordinates. There are 3 sampling coordinates used in this chapter. Normalized sampling coordinates, unnormalized, and integer sampling coordinates. So normalized go from 0, so it's like the unit interval. Unnormalized go from 0 to some number that's dependent on the width, height, and depth, and is not 1. And then integer sampling coordinates is the same, except we don't use floats. We use integers. Okay. And this is like a lot of stuff about coordinate systems. And we have some stuff about layers, L layer and sample. Final entry coordinates are used as image coordinates to perform image read after sampling calculations. Okay, so I'm not sure really what's going on. We have a coordinate system. That makes sense. That's math. We have, we seem to be keeping track of the layer. So I guess maybe like which things are in front of which things, or like which operations happen before others. And then we have a sampling. And I'm not sure how that works, but it's kind of like a compression of data, I would think, so that you use less data than you would really fully need to define it. That read an image with a sampler. Sampling operations are a set of steps that are performed on state, coordinates, and texel values. So we have validation operations, border replacement, texel reads, depth comparison. I don't know. I'm going to ignore this. So that's textures. I feel like I more or less understand what textures are about. That's a lot of implementation details that my brain's not ready for it. Here's fixed function vertex post-processing. This includes flat shading, primitive clipping, including application-defined half spaces, shader output, attribute clipping, perspective division. On clip coordinates, perspective division. And it says C coordinate transformations. So let's look at flat shading and coordinate transformations and controlling the viewport. This, I think, is maybe about some of the stuff you were asking about, like tilting in the Y direction. Sampling is, says, sampling is mapping pixel value data from an image buffer to a fragment. Okay. Is it a deterministic mapping? Why is it called sampling? So, okay, so these things are just opening up other parts of the same document. So flat shading, should be just flat shading, is a vertex output attribute. It means assign all vertices the same of the, assign all vertices of the primitive the same value for that output. Okay, so that's like color everything brown, I think. Primitive clipping, we did not care about. What were the ones we cared about? Flat shading, coordinate transformations. For a vertex, result from shader execution, which yields a vertex coordinate code position. Perspective division on clip coordinates yields normalized device coordinates. Normalized device coordinates, I think maybe device means like screen or something, or GPU, followed by viewport transformation to convert these coordinates into frame buffer coordinates. So I'm assuming frame buffer coordinates are the coordinates of the frame buffer, which are going to be pretty close to 1-to-1 for the pixels on your screen. If a vertex, blah, 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 okay. Then you can control the viewport. The viewport transformation is determined by the selected viewport's width and height in pixels. And its center, also in pixels, as well as its depth, range, min, and max, determining the depth range. Is depth like color depth? Multiple viewports are available. Number 0 to physical device limits. Okay. So, we in general have several coordinate systems going on here. We have, if we did tessellation, we had this UV coordinate system. The pixel rendering had was mapping into the like unit interval coordinate system, or a non-normalized interval. And then we have device coordinates, which I'm not really sure what those are. And then the viewport transforms it into the coordinate for the frame buffer. And all of that seems good. I'm not sure really what device coordinates are, but let's see if we can find them. That's terminal. Stop. This one. What is going on? Viewport device coordinate. No, Vulkan device coordinate. About coordinate system. These seem to be not what I'm looking for. This is a forum post. Y00 in the center of Vulkan. How about normalized? Okay. So maybe normalized device coordinates just means there's a conventional a conventional version of the coordinates that is then mapped to the actual coordinates, which depend on the size of the display and stuff like that. So I think I'm guessing that's what the normalized device coordinates are about. All right, so that's post-processing. And that's this little thing. What else can we see? Sparse memory. Resource memory association, blah, blah, blah. Sparse resources relax these restrictions and require... They can be bound non-contiguously to one or more, whatever an S name is. Okay, I don't care about sparse resources. Shaders, I care about. They represent programmable operations that execute for each work group in the corresponding stages of the compute pipeline. Only the compute shader is included in a compute pipeline. Compute shaders operate on compute invocations in a work group. They can read input variables and read from and write to output variables. And the variables they can use for transfer data between shaders, blah, blah, blah. Okay. And then shader modules contain shader code and one or more entry points. And they're selected from a shader module by specifying an entry point as part of the pipeline creation. So it's kind of like a script. Okay. I think these are relatively general. And I'm not sure that I'm not sure we're going to learn a lot about graphics processing looking at the shader documentation. Synchronization and cache control is primarily the responsibility of Vulkan. The order of execution of commands, blah, blah, blah. Okay, so this is about programming stuff, not graphic stuff in particular. Yes, I think about you to answer your question. Are the device coordinates determined in relation to the viewport? I think the answer there is that it's not. I was ignoring the word normalized for the most part and focusing on device, but I think it's mainly normalized that's doing the work, that they are in a conventional 0 to 1 or -1 to 1 coordinate system. So ray tracing uses a separate pipeline from the graphics and compute pipelines. Okay. You can, so within a pipeline trace ray, you can perform a ray traversal. Is it like setting out a single ray that invokes the various ray tracing shaders during its execution? All right. I'm not sure I'm going to look much at ray tracing. I'm going to see if there's anything. I want to see some more pipeline stuff. Render pass. Draw commands must be recorded within a render pass instance. I'm guessing draw is like, do we finally put something on the screen? Pipelines. Here's a block diagram. Is this the same thing that's on Wikipedia? Wait, what? Not found. Fine. All right, so there's something about pipeline ordering. Multiple pipeline creation. Okay, so this is about I think this is not where. I think that looking at the documentation is now having diminishing returns, because it seems like we're focused kind of down in the weeds, and I want more of like the boundary between the code you would call and what's actually being done. So the geometry shader operates on a group of vertices and their associated data assembled from a single input primitive. So the geometry shader is from a single input primitive, like I guess like a triangle, and emits 0 or more primitives and the group of vertices and their associated data required for each output primitive. So what does it do? So each geometry shader invocation has access to all vertices in the primitive and their associated data, which something 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 shader as an array of outputs. So it depends on the execution mode. Input primitive type input points must only be used with the pipeline topology of primitive topology point list. Or you can also do primitive topology line list, which I'm guessing is a list of lines or is a list of points. And then you have list with adjacency. It must only be used when tessellation is inactive, because I guess tessellation determines the adjacency in a sense itself. And you have also triangles. It can only be used with the pipeline topology of primitive topology, triangle list, triangle strip, or triangle fan. Okay, so but what does it actually do? The geometry shader generates primitives in one of three output modes: line strips, triangle strips, or points. Let's see. Geometry shader. Let's see if we can find out documentation on the geometry shader. What is the current state of the geometry shader? This is not Vulkan. Between the vertex and fragment shader, there is an optional shader called the geometry shader. A geometry shader takes as input a set of vertices that form a single primitive, for example, a point or a triangle. The geometry shader then can transform these vertices as it sees fit, sending them to the next shader stage. What makes it interesting is that it's able to convert the original primitive set of vertices to completely different primitives. So here's an example of a geometry shader. We have some input, which is what? Maybe GL in. This is probably OpenGL. So we're getting the position and we're adding a vector for it. So this is maybe just general geometric transformations. A geometry shader is an optional stage in the graphics pipeline that processes entire primitives and can generate functionality, unlike a vertex shader, which operates only on individual vertices. The geometry shader can access all the vertices and connectivity information. Okay, so I guess the idea is that it's not doing like a specific thing. It's more like it's like a hook. It gives you the hook gives you these things, and you can do whatever you want with them as long as you output the right thing. This allows for operations like layered rendering, rendering a primitive to multiple views or layers without changing render targets, dynamic particle systems, expanding a single point into a 3D sprite or a complex structure like a cube. Fur or fin generation, dynamically adding detail to models, or procedural generation, creating extra geometry dynamically on the GPU. They are generally slow on modern hardware compared to other techniques like tessellation. Okay, and so here they've added spikiness to this ball, I guess, is the idea. My take on shaders. Okay, so why don't we just try looking for images of geometry shaders? It sounds like pretty much the sky's the limit. Yeah, I guess adding spikes and fur seems to be the go-to tutorial. You find it interesting, but you're saying they find it interesting how it's executed after vertex and tessellation. So I feel like vertex is the first thing, right? And then I think it's after tessellation because because tessellation is the thing that goes maybe from like a lower polygon sort of thing to a richer representation or something like that. Vertex shaders are run once for each 3D vertex given in the graphics processor. The purpose is to transform each vertex's 3D position into a virtual space to the 2D coordinate at which it appears on the screen. Oh, okay. I didn't really know that's what it was about. Vertex shaders can manipulate properties such as position, color, and texture coordinates, but cannot create new vertices. The output goes to the next stage of the pipeline, which is either a geometry shader or a rasterizer, etc., etc. Okay. Fragment shaders. Where's our image? So vertex shaders first. Whatever input assembler is, I don't know what that is. You have some vertex or index buffer, so I guess you write to some buffer. Input, I think it's just input. So vertex is, I guess input is saying like this is maybe the UV coordinate system for your triangle. Or like imagine the camera's right above it. The reason vertex shader is rotating here, I think it's trying to tell us that's what it will look like on screen after it's rendered or something. And then we subdivide it and we do, I guess this geometry, I was confused about why this was adding a vertex here. I guess it's just because geometry can just do whatever it wants. But we're not going to subdivide it again. It's a less fine mesh because we've already tessellated. We're not going to retessellate the output of geometry. And maybe that's a thing to keep in mind. Maybe you can add a tessellation step after your geometry step if you're Pixar or whatever, and that's important to you for some reason. Okay, so that's geometry. It seems pretty open-ended. Fundamentals. I mean, I don't care about fundamentals. Okay. Execution model. Maybe I care about this. Vulkan exposes one or more devices, each of which exposes one or more queues, which may process work asynchronously to one another. The set of queues supported by a device is partitioned into families. Each family supports one or more types of functionality and may contain multiple queues with similar characteristics. I think you need examples. So device local is memory that is physically connected to the device. Device local host visible is device local memory that the host can see. Host local host visible is memory that is local to the host and visible to the device and host. Okay. So you must have run as the host, blah, blah. Okay, great. And then there's queue operations for submitting work. I guess I don't really care about that or synchronization at this point. The object model, the devices, queues, and other entities in Vulkan are represented by Vulkan objects. Great. All objects are referred to by handles. And we have object information about object lifetimes, the ABI, the command syntax, which so far is not pleasant to look at from the function names I've seen. But it's specific, the Vulkan commands using C99 syntax. Great. So base type VK bool 32 represents true or false values since C does not have a sufficiently portable Boolean. Ename, I guess enum name VK true is a constant representing the true, blah, blah, blah. Okay. That's all bookkeeping from my perspective right now. Fixed function vertex processing. I'm guessing this is vertex processing that uses the fixed functions, which I assume is fast, and we're going to ignore it. Drawing commands. Did we already see this? Ftext draw and the name provoke work in a graphics pipeline. They provoke the work. They're recorded into a command buffer, and when executed by a queue, will produce work which executes according to the bound graphics pipeline. A graphics pipeline must be bound, blah, 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 to a command buffer. Great. So what are we drawing? I thought this said ink, but it said link. Stuff about primitive topology point list, primitive topologies, point list line strips. When the primitive topology is, I guess, enum name VK primitive topology triangle list, each consecutive set of 3 vertices defines a single primitive triangle primitive according to the equation P sub I is equal to V3I plus 1 V3I plus 2. So just partitioning into triangles. And so this is saying that I think this is saying when you issue a drawing command and you pass it a set of things in a buffer, it's going to interpret them as triangle vertices. What about lines? When it's set to lines, it's going to interpret them as endpoints of lines. What about line strips? When you set it to line strips, is defined. One line primitive is defined by each vertex, and the following vertex. Except now, here we did so element 0 and 1 would go to V0, V2 plus 1, V3. And here it would go to V0, V1. I guess. So it's just a different, a different splitting up of the lines. And I'm guessing here, these are separate. These are partitioned separately. And here, I guess Vi plus 1 is going to be, so P of I sub 1 is going to have its the let's say left end, the first end of its line is going to be the same as the last end of P sub I. So that's the sense in which I guess they're strips. They're like connected, I guess. A triangle fan should be like a geometric fan. Let's see if we can triangle. Like this, I'm guessing. These are just different shapes that you can do. So I guess the idea of a triangle fan is you have a single point that's singled out, and maybe that's what V0 is, and then everything else varies. Okay. So these are different things you can draw. Can you draw a circle? I guess circles don't really exist. And then we have dispatching commands. Okay. I feel like I've learned a great deal. I don't know if we didn't really look at any code. This may be the first one we've looked at that didn't have real code, but is that a crime? It might be a crime. How about we look at a little bit of code? How about circle example? How to render circles. Triangle fans versus code in the fragment shader. Why are you talking about triangle fans? How about Vulkan API examples? C++ examples. We'll just look at one just to see that we did. Will there be a part 2? I don't know. You mean of this? Should there be a part 2? Possible. The problem is I don't really know where to go next. I also don't know where to find these actual examples. How about examples folder? Bloom, compute headless, compute in body, descriptor sets. I want something simple. Pipelines. These are going to be too big. Stencil buffer. How about triangle? Triangle.cpp. Basic indexed triangle rendering. So we're going to include some Vulkan stuff. Max concurrent frames is 2. And what do we have? We have a vertex struct with positions and colors. Color is a float. Oh, no, sorry. I was thinking this was a list of vertices, but this is a single vertex with a single 3-dimensional color and a single 3-dimensional position. Yeah, sounds good. Then we have a vertex buffer and attributes. We've got this VK device memory with VK null handle to the device memory for this buffer. Why is it null? I don't know. And a VK buffer. And then an index buffer, which is the same type here, except we've got a count for indices for the index, I assume. I don't know why. I don't know how these two, the top half of the index buffer and the vertices struct are different, but they might be being used differently. In a uniform buffer block, whatever that is, we've got again memory and buffer and some descriptor set. The descriptor set stores the resources bound to the binding points in a shader. It connects the binding points of different shaders with the something, something, something. I just scrolled past it by accident, but I'm just ignore it. And then we have shader data. And the shader data has a projection matrix, a model matrix, and a view matrix. Okay. So this might be like mapping into the coordinates for modeling. I'm not sure what model matrix means. And I'm not sure why projection matrix and view matrix are different. This may be just a matter of normalization or something. We have a pipeline layout. A pipeline. Yeah, this is verbose. I'm going to see if I can skip down here. So we have a Vulkan example, which extends Vulkan example base. I'm guessing this might be part of this repo as opposed to like a Vulkan example thing that lives in the Vulkan API. And it's got a title. We don't use the UI overlay. Okay. We've got a camera. We're setting the position to some place 0, 0, negative 2.5. And then there's no rotation, explicitly setting it to 0. And then we're setting some perspective thing. 60. I don't know what 60 is. Maybe frames per second. I'm not sure. But we're also giving it some floats. This is, I guess, maybe some just perspective matrix. I'm not sure. This is a destructor. Get memory type index. This function is used to request a device memory type that supports the property flags we request. We can create synchronization primitives. Okay, now we're going to do, this is synchronization stuff. I'm going to skip it. Create command buffers. I don't know what CI stands for, but we're something about a command pool, or maybe we are pooling commands. And create info, queue node. We're like manually managing the queue. This looks a bit fiddly and there's maybe mental overhead. Lots of things to get wrong, I would think, if you're doing all of this manually. And then we create a vertex buffer. That's probably going to initialize the thing. I don't know. Note on memory management in Vulkan in general. This is a very complex topic, and while it's fine for an example application, blah, 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 blah. Okay. So we've got a vertex buffer. It's got some vertices. Three things of 2 vertices each. So I guess these are maybe lines, possibly. And then we compute the buffer size. We set up indices by creating an index buffer with 0, 1, and 2. We allocate some memory, more memory stuff. We have a staging buffer. And then, I don't know what any of this stuff is doing. Info CI, buffer usage, vertex buffer bit, create buffer. Wow, this is crazy. I don't think that there's any chance. Is this how it always looks? Create descriptor sets. But where are we actually using this triangle? Let's see if we can find, was it viewport, view, transformation? Projection matrix. All right, so here we're setting the projection matrix to the camera matrices perspective. We're setting the view matrix to the camera matrices view, and the model matrix to whatever, like a 4-dimensional matrix with ones. Is that just maybe the identity? And then what do we do with it? That's called shader data. And then we must pass in the shader data to some call. Like buffer image size, blah, blah, blah. We're calling size of on it a lot. Yeah, okay, we're just passing it here. We're mem copying into the uniform buffers. So copy the current matrices to the current frame's uniform buffer. I don't know what uniform means in this context. Since we requested a host coherent memory type for the uniform buffer, the write is instantly visible to the GPU. Okay, this is, I guess, sending it to the GPU because of the setup. And then that's the shader data. Okay. Then we're going to build the command buffer. This, I guess, we're maybe about to start drawing. Buffer begin info, v structure, buffer begin, render pass, vk. Yeah, I don't know. This is too complicated. I thought we would see things that looked more like drawing. This is mostly, like most of the code, if you kind of sample it randomly, is stuff about managing Vulkan, which is not entirely surprising. This stuff has to be happening somewhere. I'm a little bit surprised it's not more abstracted. Let's see what is about you saying. The shader data is used in the vertex bit. Okay, a bit of a misleading name. It's a coordinate transformation, I recall. Being view model projection. Okay. Uniform is a variable that's the same across all shader execution in pipeline. Okay. So, but this isn't, for example, it's not clear where to see the stuff that we were looking at. So I'm wondering if we so I'll look up examples again. Maybe this is just specific to this this repo. Here's an example of some Vulkan thing that's on vulkantutorial.com. I don't know if it's associated with the Vulkan people or not. But this has a Hello Triangle app. And we're going to call app.run. And the Hello Triangle application has init Vulkan main loop and cleanup. They do nothing. So what are we going to, where's run? Yeah. Okay, so run is there. I guess they're going to build this up. They're going to implement init window. Okay, so this is kind of building up an example. And is this the full thing? So GLF window, so this has some window hints that we're calling create window. And then we're calling poll events. Vulkan works perfectly fine without a creating window, blah, 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 blah. What is GLFW though? But what is it? What is it? Vulkan GLFW. Good luck for creating a Vulkan window surface with GLFW. So it's some header file for creating windows. And then what is the main loop here doing? This is just the base code. It's not instance. Creating an instance. The very first thing you need to do is initialize the Vulkan library by creating an instance. But you already did a bunch of work. This is part 2 of the tutorial. Need I remind you? So create instance is going to say app info is a bunch of stuff, giving it some names and metadata and stuff like that. And this tutorial seems to be just different from the other example, mainly by building things up in functions and walking you through it. And that seems reasonable. But let's try, I'm programming a game in Linux and want to use the Vulkan API. Should I use Vulkan directly? or rely on a library that abstracts, that simplifies Vulkan. So you don't have to use the Windows, I see. Windows in the sense of the Windows operating system. So if you want to ship a game quickly and focus on gameplay, use a higher level Vulkan abstraction. So if you want full control, you can do that with using Vulkan directly. But you can also use something on top of Vulkan, such as BGFX, VK Bootstrap, Vulkan HPP, SDL3 plus Vulkan helpers. I feel like I've never seen any of these. So walk through the coolest and most popular open source video games and game engines that use Vulkan, and tell me whether they use a library for Vulkan directly. Make a table. Got it. I guess I was mainly asking if GLFW is Windows specific, but who knows? I'm guessing it's probably not. So ChatGPT is going to do this research for me, and it's going to take a while. I'm going to ask DeepSeek to do the same thing because I never ask DeepSeek anything. I'll call it the deep think, which I think is different from deep research. And I guess I'll have. So Vulkan is Hephaestus, right? The god of making things out of iron. Wait, there's no way Vulkan is. There's no way Vulkan goes to the 3D library, is there? Oh, it's because there's a K. It's because it's a misspelling of Vulkan. Not a misspelling, but maybe a different spelling from a different language. So here's Vulkan. Volcanos, the god of fire, including of volcanoes, deserts, metalworking, and the forge in the ancient Roman religion. Cool. And his Greek equivalent is Hephaestus. Draw an image of Vulkan forging a GPU in a volcano underground base. Beautiful cinematic lighting, high detail, emotionally evocative, with emotionally spelled incorrectly. See if you can do that, Yemeni. All right, so the ChatGPT made this table. It claims Godot uses raw Vulkan. Engine is rewritten to use Vulkan backend. It says everyone's using raw Vulkan. These are game engines. I don't know if I trust all this. So what about is Blender on here? What about Blender 0AD? Is that, I don't know if that uses 3D graphics and other games, not just engines. Vulkan did it in a cave with a bunch of scraps. Oh yeah. This is pretty good. I don't know what's with this fiery thing up here. I feel like it's a little bit too cartoony. Less cartoony and more like a realistic photo. Grittier. Okay. So Super Tux Cart has experimental Vulkan. It seems like most people are using Vulkan directly, at least according to this ChatGPT mind test. No Vulkan, OpenGL only. Okay, so let's ask. So let's take a look at the Godot engine and see if we can find any Vulkan code. I don't know why my head's so low. I guess because I changed my camera. All right, Vulkan. So we do have Godot Vulkan, OpenXR Vulkan extension, context Vulkan, blah, blah, blah. Context driver Vulkan, rendering context driver functions. So is this calling? Yeah, this maybe looks low level. VK physical device features. Physical device features is set to the empty thing. Okay, this seems like it might be actually ChatGPT was possibly correct. This is long. Pipeline cache header, command bind pipeline. So I wouldn't. I feel like this is not much. This obviously isn't the whole thing. There's more stuff here, but I feel like this is not much more work to understand than the triangle example. That may be wildly inaccurate, but that's just my sense. It's just my sense. I think it's gonna be. They're both going to be hundreds or thousands of lines, and this is going to be doing some kind of rendering for a whole game engine, as opposed to just like a couple of triangles. Let's see if we can find documentations for Godot engine Vulkan. About, oh, with a K, sorry. That's a crazy Vulkan. Blah, blah, blah. Yeah, so it sounds like they're using both for now. Okay. So I'm going to just check in with my Vulkan image, and then we're going to head out. That doesn't look anything like a... Let's see if ChatGPT will do a better job. I have found that once Nano Banana picks like a style, it refuses to leave it. I don't know if that's just a defect in my prompting or something else. But, you know, these two are virtually indistinguishable. What do you say? But I can probably transform it into something else. Turn him into mermaid. I forgot how slow ChatGPT image generation is. See, you can make him a mermaid, and he could be underground, but it's like the same image. Draw an image of the god Vulkan. But make it the craziest thing you've ever seen. Like, so crazy, you'd have a hard time describing it to a friend. It's really wild and out there. And changes your entire perspective on life. Their AI seem a bit overfitted lately. Oh, you mean Google? So much confidence on stuff it doesn't know to argue. My based on it's okay. Based on reading between the lines in some of the bugs for the Gemini Cly, my guess is that Google has more demand than compute, and is I don't want to say that they've nerfed their AIs, but they seem more constrained. And my guess is, just completely speculatively, that my guess is just completely speculatively that they are, since they're a bigger company, they can't like do the sort of really speculative investments in infrastructure. Any investment any investment they make in like GPUs and stuff has to have a higher chance of paying out than say OpenAI. And I think that they are probably working hard on making inference very efficient, and they think that they're going to that Anthropic will go away, or maybe be sold to a like second or third tier player, and that they're going to outlast OpenAI, and are maybe going to do a couple of rounds of ensuring that that inference is more profitable before doing additional build out. That's just kind of a guess. All right, so here's what ChatGPT came up with, a realistic image. Looks good, but make it really crazy. Like, imagine if Goya painted it while taking all of the drugs. Yeah, so like this is not. Maybe this would be a better prompt for like Mid-Journey. We've got floating. We've got this. His head is a universe, but there's also like some kind of head up here, and then there's like these kind of ghostly beings. He kind of reminds me of Unicron from the Transformers movie. Here's Unicron. He's the size of a planet. they're very micro. Yeah. All right. I'll see how long this takes to ChatGPT. Okay. So the DeepSeek is also saying that that most of the game engines and stuff use Vulkan directly. And maybe the problem with the examples I was looking at was that there's a bunch of one-time setup, and that one-time setup doesn't pay off for a small example, but does pay off well for a game or a library or something. Creation might take a moment. Yeah, do it. Let's go. I have a feeling it's just going to hover here at like, what is this, 90% finished? Okay. Fine. I've changed my mind. Make it into a 1970s style, about 1950s style cartoon. My guess is Gemini Flash is just going to render basically the same image. Yeah, it looks a little bit. It's the same image. It looks a little bit like a comic book cover. ChatGPT. I'm guessing that ChatGPT does a better job of taking feedback. What if I say give him 6 arms? It's not going to do it. The AIs are just giving up on us. As if we can find Vulkan libraries. There's this awesome Vulkan thing. I mean, if there's going to be a part 2, I feel like I need to know. Maybe looking at the Godot implementation or some other implementation that's calling Vulkan would be the right thing to do. Vulkan barriers explained. Say hello to a new rendering API in town. ARM, Vulkan best practices. We didn't really look at the, what is it called, Spurvy? I don't know what Spurvy code looks like. Here's the Spurvy language ecosystem. Support for Spurvy environmental specs. So if it's this ugly green color, it's OpenCL. OpenCL, that's different from OpenGL, right? Open Compute Language, is that like a CUDA? Open Computing Language is a framework for writing programs that execute across heterogeneous, blah, blah, blah. Influenced by CUDA. I think maybe it's like an open CUDA sort of thing. This makes it look like it's a medical test, this logo. But whatever maybe this is cross in the sense of cross compilation. Metal shader language, HSL, GLSL. Is GLSL Linux? OpenCL is for compute. Yeah. Okay. Thank you. I don't know what it is. Some shader language by the Koorosh group people. And then over here we have what? Some LLVM stuff, which you can use, I guess, with MLIR. So TensorFlow, PyTorch, computing stuff over here. Somehow Clang is involved. Whatever ChipStar is, which gives us HIP and CUDA. That's the AMD stuff. ChipStar. Maybe ChipStar is a project. Shit, software engineer. Wait, what? You're saying this is insane? Or something else that was on the screen? And then whatever this is, whatever slang is, I don't know what slang is. Let's try GitHub. slang. Shader slang. Making it easier to work with shaders. Okay, so these are people who... slang is a shading language that makes it easier to build and maintain large shader codebases in a modular and extensible fashion. Okay, so these are, I guess, different people that use parts of Spurvy. Great. And Gemini's not even going to try. This is just the... I mean, this is just the face of that one Goya painting, which I guess I won't show because it might be unsettling. But we do have the ghouls rising from the flames and a kind of maybe Van Gogh style, crazy bright colors. It's not bad. All right, that's all. That's all for me. Looking at the Koorosh group APIs. What are they called? The Vulkan APIs. We didn't see much code, but I think I have a better sense of kind of the details of how the renderings work, and how information flows into the pipeline. And then if we were at some point, which I'm sure eventually we will do, I'm not sure how soon. Maybe it depends on how much demand there is. But if we take another look at code that's calling Vulkan, then I think what we'll have to wade through is all the sort of setup and tear down and synchronization barriers and work groups and kind of all the bookkeeping involved in synchronizing a pipeline of execution. And that stuff is, in a sense, there's a sense in which that's important and fundamental to the graphics rendering pipeline, but there's another sense in which it's not. It doesn't answer the question about rendering pixels on screen, so I've sort of glossed over that. But it looks like from the few code snippets we've seen that all of that's kind of interspersed with the rest of the graphics code and will be like a big part of any library use of Vulkan. So with that, I will leave you. Have a good weekend if you're watching this on a Friday, like we're recording it. If not, have a good week. And I'll see you next time. This is Answer Everywhere.